Hello everyone, welcome to the next lecture of bipolar junction transistors. We are talking about the bipolar junction transistor based amplifier circuits. In the last lecture, we discussed how we can use a bipolar junction transistor as an amplifier, how we can operate that in the active region, how our voltage transfer characteristics looks like. We want to make sure that we will operate the transistor in the cutoff in the active mode, and our changes in the input voltage VBE should not move the transistor into the saturation region or the cutoff region. Okay, so let's talk about, so our today's lecture is going to be focused majorly on the small signal operation of the bipolar junction transistors, and we're going to drive different equations for the voltage gains specifically for the small signal operation. So let's talk about it. All right, so small signal analysis and models. Here is our circuit again. NPN transistor being used as an amplifier in the active region. We want to make sure that our collector to emitter voltage should be greater or equals to 0.3 volts. Our collector to base junction should be reverse biased, and emitter to base junction should be forward biased. This is our biasing voltages at the quiescent point. This is a time varying input voltage that we need to amplify, right? Similarly, our output voltage VC is going to have two components. One is the DC component plus one is the time varying component. Similarly, our collector current is going to have two components. One is the DC component and one is the time varying component. So this will be the summation of these two components. So we are going to discuss all of these components in more detail. Okay, so let's first consider the DC bias point at which we bias our transistor. So while discussing that, we are going to assume that our time varying component of the input signal is 0. So we are setting our VBE to 0, and we are going to find out all the DC voltages and the currents. So here are all the voltages and the currents. Our collector current, DC collector current, is given by scaling current, exponent of VBE over VT, which is a biasing potential for the emitter to base junction. In order to make it forward bias, we have seen all of the equations before, right? Our emitter current equals IC over alpha, where alpha is the common base current gain. Our base current equals IC over beta, where n is usually very small. Our beta is known as common emitter current gain, and this is a value that we have seen in the last lecture. This equation we have seen in the last lecture as well, where our VCE here, right, so this is the DC component, this one, this should be equals to VCC minus ICRC. So whatever the changes that we have in VBE, that will change the collector current. So our product ICRC will change, and that will be reflected in the output biasing voltage VCE. So these are the biasing DC values of the currents and the voltages when our time varying components are neglected. Now let's apply our time varying small signal. So let's apply the small VBE value on the top of the DC biasing voltage. So this was a DC bias voltage at the emitter to base junction, and now we are also applying this time varying component. So our in total instantaneous time varying voltage at the input will be this value of VBE, which is a summation of the DC voltage plus the time varying input component. So our collector current will be, now we are going to replace this value of the VBE with the summation of the two values, right? So this was our total collector current will be equals to the total value of the input voltage, and the total instantaneous input voltage is this VBE plus VBE, the DC value plus the time varying component, right? So we ended up replacing it with this one, and now we can easily expand these two components separately, which will come out to be this. Now we can easily realize that from this component is that this equation is simple IC. So we can replace this with the IC. So this is the total value of the collector instantaneous current that we get, which is the DC current, plus this extra component that appears over here. Now what we can do is we can do an expansion of this equation. So if we do an expansion of this equation, considering our time varying component to be very smaller than the threshold voltage, if we will make this assumption, and we're going to realize that this is a small signal approximation, or the condition for the small signal approximation for linear operation, then our expansion of this exponent is going to be 1 plus VB over VT. We can also expand this equation. So this is a small signal operation condition. So now our IC would be equals to IC plus IC VBE over VT. Now we will realize that this is the total collector current that is appearing over here. It has a DC component and it has a time varying component. So this small IC is this time varying component, which is due to time varying base to emitter voltage that is applied over here, right? So this IC is over here, where it's a DC component and the signal time varying component, VBE over VT. Okay, so let's discuss about this time varying collector current in more detail. So let's look at that. So our time varying IC is IC over VT, VBE, signal component. So we have IC equals IC VT over VB. Now if I look at this equation closely, this equation relates the changes in the input voltage base to emitter, which is applied at the base to emitter, superimposed on the biasing VBE voltage, will produce a corresponding changes in the collector current represented by IC. Again, this is superimposed on the DC value of the collector current IC. All right. So another thing that we can do is, if we look at this parameter, IC over VT, this looks like a transconductance parameter. This is the transconductance parameter of a bipolar junction transistor, and can be represented by the value GM. So GM, so we could also write this thing as IC equals GM VBE, where GM equals IC over VT. All right, so where GM is a transconductance and GM can also be represented by IC over VT. All right, so please remember these equations. These equations are going to come in handy in solving the problems and in the later part of these lectures too, right? So our time varying collector current, or the signal component of the collector current, is equals to the product of the transconductance of the bipolar junction transistor and the signal component of the base to emitter voltage that is applied. And another representation, and from this equation, looking at this equation in detail, we also see that the transconductance parameter equals to the biased collector value of the collector volt current, the DC value of the collector current, to the divided by the thermal voltage VT. Okay, so this is how it looks like currently. For example, over here, so this is the plot of this equation. Our output is IC. Not this equation, this is just the time varying component of the collector current. So this IC is the total collector current and the total VBE, which is a summation of the bias value plus VBE, and this collector current is a summation of DC collector current and the small varying component. So this IC is GM VBE. All right. So this is the exponential relationship of the collector current to the VBE, and this IC can also be represented as IS VBE over VT, right? So it has an exponential relationship with the scaling current. Okay, so this is the plot, exponential plot of the collector current to the input voltage. And as we can see over here, we bias, for example, if we select this quiescent point Q at this point, right, and then if we make a tangent here, so let's look at the input and the outputs, and then what we do is we pick these points, and now as we get these input signal varies, as our input signal varies, look at the changes in the output signal. Our output signal is amplified because of this exponential relationship. So this is our voltage controlled current amplification, right? So we have this kind of a transconductance amplifier. So we connect a resistor RC to get a voltage amplification. So another important thing to look over here is our slope of this line at this quiescent point. So our quiescent point is our bias point. Our bias voltages and the currents are IC and VBE. So the voltage, the input voltage, bias voltage is VBE, and the output bias collector current is capital IC at this quiescent point. So if we plot a tangent at this quiescent point Q, then the slope of this quiescent point will give the value of the GM. So we can also represent this GM as a derivative of IC to the derivative of VBE at Q point. And what we have at the Q point, our IC equals capital IC. Right? Okay, so this is the value of the GM over here, which can also be seen over here. All right, so two important things that we can learn from this plot is, again, looking at the linear operation of the transistor. If we will bias the transistor at Q point and make sure that our changes, our time varying or the signal component of the input signature or input signal, or time varying component of the input signal applied at the base to emitter junction is small, our output changes in the current will be linear. So for a linear amplification, we want to make sure that our changes, our swing or our changes in the input voltages should be small enough. So what will happen when our changes will be larger in the input voltages? We will start to see non-linearities in the amplification. And we have also seen in the voltage transfer characteristics that we have the limitations on the negative and the positive swings that are allowed. If we are going to have a high positive swing in the input voltage, then our transistor will move into the saturation region, and if we are going to have a high negative swing, it will move into the cutoff region. So we want to make sure that our swing voltages are such that we are still operating in the active region of operation of the bipolar junction transistor, and we also want to make sure that they are small enough so that we will get almost a linear amplification of the input voltages. Okay, so let's derive some more values of these currents. So by now we have looked at the biasing voltages and the currents. Then we started with the collector current and we looked at the DC value of the collector current and the signal component value of the collector current. So let's look at the base current now. Okay, so we know that our base current equals collector current over beta. All right, so this is what we can get. So our base current is collector current over beta, right? And we know that our collector current from here, IC equals DC value of the collector current plus the signal component, right? So we can, coming back here, so you can also write it over here, right? For example, IB equals 1 over beta into IC plus IC. So essentially this is what we are doing over here. So we are, we have 1 over beta is common, and then we have our DC IC value of the collector current and the time varying component of the collector current, IC over VT into the base to emitter signal component of the base to emitter voltage. Similarly, looking at this equation now, right? So if you look at this equation closely, now this equation also has two components. One is a DC component and one is a AC component. So this means that your base current also has two components now, the DC base current and the time varying or the signal component of the base current, IB, right? So these are the two components where capital IB is this, small IB is this. All right. Right, where IB, capital IB, or the DC component is equals to IC over beta, and this small IB is equal to this component, right? So this can be given as 1 over beta IC over VTE into VBE, right? So this is the value of the signal component of the base current. Now, interestingly, if you remember our IC over VT, this thing was equals to GM. Where we are getting this from this one, right? So we find out that the transconductance is equals to collector current over bias value of the collector current to to the thermal voltage. So I'm going to use this thing over here. So our new value of base current will be equals to 1 over beta GM, 1 over beta GM into VBE. Right, so this is what we get. So it will be, so the base current will be GM over beta into VBE. Again, this is a base current. Our beta is called as a common emitter current gain. Again, where our emitter is common between the base and the collector. So if we in this configuration with a common emitter, if we look into the base terminal, then we are going to see a small signal resistance at the base terminal. So the value of that resistance can be determined as, all right, so the important thing is that again, so our beta is a common emitter, so we are looking at the common emitter configuration. And in the common emitter model, if we look into the base terminal, our resistance in between the base and emitter is denoted by R pi, and we're going to discuss this in more detail shortly as well. So our resistance R pi is a common emitter, is a common emitter resistance, is a resistance in between the base and the emitter in a common emitter model, to be more precisely. Okay, all right, so so this means that our R pi should be equals to E VBE over IB, right? So our R pi should be equals to VB over IB. So this is coming from this equation, right? So we can do VBE over IB equals GM over beta. Now this VBE over IB shows a value of some resistance, right? And this is in the common emitter model. So this resistance, which is equals to VBE over IB over here, sorry, will appear in between the base and the emitter model. And since we are talking about the common emitter gain, so it's in the common emitter configuration. So in a common emitter, so conclusion, common emitter configuration, our value of VB over IB represents a resistance that comes in between emitter and the base. Okay, and is denoted by R pi. So we have an R pi which is equals to VBE over IB, and or R pi can also be written as beta over GM. I think I did this, wrote this equation. So over here we have VBE over IB should be equals to beta over GM. All right. Okay, so this is the value that we got. R pi equals to beta over GM. So let's consider this thing. Now we know that our base current is equals to IC over beta, and these are the biasing values of these base current, right? So our IB equals IC over beta. This is probably one of the very first few lectures when we were talking about the flow of the currents, the flow and the amounts of the currents that were flowing through the transistor, bipolar junction transistor, in the active region when the emitter based junction was forward biased and collector based junction was reverse biased. So this was one of the very early lectures of the bipolar junction transistors. Your base current is equals to the collector current divided by the common emitter gain, and usually very small. And this equation, GM IC over VT, is again coming from here. All right, so considering these two equations now, we can replace the value of GM and beta in this equation. So let's replace this value over here. So our R pi equals beta, beta equals IC over IB, over GM equals IC over VT, so cancels, VT over IB. So your another equation for the resistance looking into the base to emitter resistance looking into the base will be equals to VT over IB. So another equation to remember. All right. So we ended up, so in this entire slide, but we started with finding out the values of the base current, right? So we ended up finding the value of the base current, and we said that value of the base current is equals to the summation again of the bias DC value plus the signal component, smaller IB. We ended up putting the values of the collector current over here. Then we looked at the base current. The signal component of the base current is equals to this. And then we ended up deriving this equation. The resistance in between emitter and the base, looking into the base in a common emitter model. So now let's look at the emitter current. So we have looked at the collector current, base current. Now let's look at the emitter current and the resistance at the emitter too. All right. Now we know that again our IE equals IC over alpha. We have seen this equation multiple times now. So our IC, again our IC equals IC plus signal component IC. So we are, so this is the DC component, this is the signal component. So our IE can be, again, this is a DC component here, and a small IC over alpha is the AC component here, or the time varying component here. Right, so now we know that our small IC is equals to, where it is, this one, IC VT over into VBE, IC over VT into VBE, IC over VT into VBE. Okay, so our emitter current will come out to be, so the small value of the emitter current, or the signal component of the emitter current, will come out to be 1 over alpha IC over VT into base to emitter AC component. So this is the value of the IE that will come out, and now we know that this capital IC over alpha is this DC value over here, right? So this thing is capital IE, right? So that is why our small, let's do it over here, our small IE will become capital IE over VT, capital IE for this IC over alpha divided by VT into VBE. All right. Right, so this is the equation that we get. IE equals this. IE over VT into VBE. Now, if we go back to the previous slide, right, this equation looks very similar, right? We had a going back, right? So we have 1 over beta, IC over VT and VBE. So we have a base to emitter and IB, right? And from there, we ended up finding the values of the resistance in the emitter. Now, if I will look at this equation again, I can rewrite this equation as VBE over IE equals VBE over IE equals VT over IE. Now this VBE over IE value represents again a resistance value. This resistance is for a common base model while looking into the emitter terminal, right? So this is denoted by RE. So our RE equals VBE over IE. It also equals VT over IE, right? So RE equals VBE over IE. And the emitter resistance can also be represented by thermal voltage divided by the bias value of the emitter current. Okay, so let's derive another. Now I'm going to derive another equation for the same emitter resistance, another representation. In order to do that, we need this RE equals VT over IE. We have seen that GM equals IC over VT. So I'm going to use these things to find out the value of RE. All right, so what we do is we are going to use these two values here. So our RE equals, find the value of the VT from here, VTIC over GM over IE. Okay, so now we know that, okay, so this is, what do we have here? Our IC over IE is, yeah, our, for the DC part, our capital IE equals IC over alpha. So we have IC over IE equals IC over IE equals alpha. All right, so this is our IC, this is our divided by IE. IC over IE into 1 over GM equals IC over IE equals alpha over GM. So this is the new value of the RE that we can also have. Again, we know that alpha usually equals to beta over beta plus 1. Beta values are very large, so alpha is approximately equals to 1. Very close to 1. Approaches 1. So that is why it can also be written as 1 over GM. However, also remember this equation. This is the emitter resistance in the common base model. All right. So interesting thing that we can also kind of find out the relationships in between the emitter resistance and the base resistance, and emitter resistance and the base resistance. So in terms of the emitter resistance, we have our VBE is common, right? So our VBE over here is REIE, and over here VBE is R pi IB. R pi IB VBE. So I can equate these two equations together. So VB equals IBR pi IERE. So we can easily write this thing, right? So our RE IE equals R pi IB, from where if I can find out this R pi, this will be RE into IE over IB, right? So you can easily write down this equation like this. So this is another relationship in between the both resistances. R pi is the base resistance, RE is the emitter resistance. So they are both related with the ratio of this IE over IB. And if you remember the ratio of the IE from one of the earlier lectures, the ratio of the IE over IB equals beta plus 1. So this can also be rewritten as this equation. So please remember these equations. These equations are also will be available to you for your exam, so you don't need to worry about memorizing any of these equations. However, this would really come in handy if you know to perform your experiment or to do your problems faster. Okay, so let me show you a couple of models now. Oh, okay. Again, we run into this. All right, these are the two models. Let me rub this too. All right. So this is what we have been talking about, right? This is a common emitter model. So in a common emitter model, looking into the base, the value of the resistance is R pi, base resistance, and the value equals to VBE over IB. In a common base model, the RE is the resistance looking into the emitter terminal, and the value is VBE over IE. So this is what we kind of representations of the models, circuit models of the common of the emitter resistance and the base resistance for the common emitter and the common base models. Okay. So we started with, in the small signal operation, we find out all the values of, again, the DC bias point. We find the collector current, the base current, the emitter current. Now let's do the final thing as find out the value of the voltage gain. We know that the value of the voltage gain, or any voltage gain, has to do with the output voltage to the input voltage. Our output voltage is, look at the circuit, this value, the VCE. Again, it is a summation of this capital and this signal component of the VCE, right? So going back to the circuit again, so this value of this VCE equals VCC minus IC RC, and this IC again is IC plus IC. So let's do this thing now. So our total output voltage VCE equals supply voltage minus IC. This is the total collector current. And so we can expand this total collector current as this, the biasing current and the signal component of the current. And now just expand this equation, VCC minus ICRC, and this signal component comes out to be separate when you open up these brackets in the equation number 2 here. All right. So once you open up the bracket, you will realize that this component is the biasing or the DC value of the output voltage. So this will come out to be VCE, and then you're going to have a time varying component, or you have a signal component which is equals to small IC and the resistance RC. Right, again this component ICRC, right, so essentially your VCE should also be equals to capital VCE plus small value VCE, right? So this small value of VCE equals minus ICRC. So this is the signal component, the time varying component that is superimposed on this DC value of the output voltage VCE. All right, so this is the superimposed voltage. Okay, so we can also derive these equations. By now we have this thing, our VCE equals minus ICRC. Again, this collector current, going back to the slide over here, our collector current is GM into VBE. So we can do this thing, GM VBE into RC. So this thing is over here, right? Okay, and now again, this is our input and this is our output. So we can divide the two. VCE over VBE equals minus GM into RC. This is the value of the voltage gain for the small signal operation. All right, now we know that the value of the GM can also be represented from here from equals IC over VT. So we can also do the similar thing here. So we can replace this value over here, and our new value of the voltage gain would be equals to minus IC over VT into RC, another expression of the voltage gain. So depending on whichever the values are given in the problems, in the circuit problems, you can use those. You can use the relevant equation to solve that. Right, so we did this thing using this value. Here is our another value of the voltage gain that we derived over here. Okay, great. All right, so we also ended up finding the voltage gain. Now let's look at the so the final component of our lecture today is looking at the equivalent circuit models for both common emitter and the common base. So we're gonna start with common emitter models, right? So this is a common emitter model. It's an NPN bipolar junction transistor being operated in the active region. Just looking at this, we can realize that this is a voltage controlled current source. We have a base current, collector current, emitter current, right? Our emitter to base junction should be forward biased. This is a signal component of the input voltage that is superimposed on this biasing voltage to forward bias this junction. And R pi again is the resistance, is the base resistance looking into the base terminal, and this resistance appears in between base and the emitter, right? So we ended up finding the values of all of these things. For example, right, so this is a collector current IC. We know that IC equals GM VBE. You can see this value again from here. IC equals GM into VBE. Other values, we can find out the values of RT. These values of the R pi can be so this is the base resistance, right, in a common emitter model. So the base resistance in the common emitter model is equals to beta over GM or VT over IB, right? So beta over GM or VT over IB. All right, so this is the voltage controlled current source. We can also convert this or into a current controlled current source. So this model represented over here is a bipolar junction transistor as a current amplifier, in which again our our input is the base current, our output is the collector current. Our resistance is again the same, the base resistance R pi, signal component of the input voltage. And we ended up doing this GMVBE into beta times IB, because we know that the base current IB equals collector current divided by beta. So collector current into beta times IB, collector current was GMVBE. So we can alternatively write the collector current term as VGM and GM multiplied by the signal component of the base to emitter voltage, which is VBE. So when we write this, so this will become a voltage controlled current source, and if we use this equation, this will become a current controlled current source. So we can represent it either ways. Important thing to remember and note down that these models, the common emitter models for a bipolar junction transistor, are known as these hybrid pi models. So just remember this thing. And these are for the small signal operation, because we are looking at this time varying signal component of the voltages and the currents. All right, let's look at the common base models. The common base models over here are known as the T models. The T models because it looks like a T, right? This, right? And our base is over here, collector is over here, emitter is over here. So this looks more like a T model. Okay, so in a common base model, we know that our resistance, we need to find the resistance looking into the emitter, right? So if you remember this circuit, for a common base, we are interested in finding the resistance over here. So emitter resistance, which is RE. All right, so this is again our signal component of the bias input voltage that is superimposed on this biasing voltage to forward bias the junction. This is the RE, the emitter resistance. Our values of the emitter resistance, these equations are coming from what we just derived, right? So these are the two equations, VT over IE and alpha over GM, right? VT over IB and, VT over IE and alpha over GM. Again, this is a voltage control, and our collector current, we know that, right? This is GM into VB. So this is a voltage control current source. You can also represent it as a current control current source using the same common base model. Interesting thing, how will your value change over here? We know that, let's go to the emitter current. So we know that emitter current equals IC over alpha, right? So our emitter current equals IC over alpha. So our IC equals alpha times IE. So we end up putting this, right? So IC equals GM VBE, and it also equals alpha times IE. So we can alternatively use these equations. We can also derive these equations from here when we know that our IC equals GM VBE, and we know that our VBE, this value in the common emitter model, right, from this, our VBE equals IE into RE, right? So GM VBE equals IE into RE. So we can do GM into RE into IE, and GM into RE is over here. RE equals alpha over GM, alpha equals GM into RE. So you can replace over here. Collector current terms is alpha times IE. So you can also derive the same equation of the collector current, alpha times IE, using this analysis. All right. So with that, this was our final part of the modeling of the circuits for the bipolar junction transistors. Right, so for example, this model again is a current amplifier, current control current source. This is a transconductance amplifier, voltage control current source. So anyways, this was a final part of our lecture today. In the next lecture, we are going to discuss find out the voltage gain values of the three configurations: common emitter, common base, and common collector. And after that, we also are going to do a few examples of those configurations, and that will be the final lecture of the section and of the course as well. So with that, thank you so much for today's lecture, and I'm going to talk to you in the next lecture. Thank you. Bye bye. Have a good day. Bye.